This meeting is being recorded.
In section 15.5, we're going to take a look at the next characteristic of our signals that are produced with NMR spectroscopy, this characteristic of chemical shift. And when we look at our chemical shift, as it's referred to, we need a reference point or a zero marker. So this standard of TMS or tetramethylsilane is commonly used as our internal standard. So this produces what is commonly zeroed out as a zero signal because these protons in this structure generally produce a frequency much lower than other organic compounds. So that's how we can utilize this as like a zero marker, or you will not expect to see a signal below this. So we utilize this 1% TMS as a standard, in addition to any solvents that are used. And the shift that we're referring to is how far a signal for a proton will appear as compared to TMS. So if we have a 0 point, whatever the frequency found to be from or observed from TMS in hertz, divided by our operating frequency of our instrument, also in hertz, that would give us this delta, this value that we consider for each of our protons. So that chemical shift, again, is the observed shift from TMS in hertz divided by the instrument's operational frequency. So say we have benzene specifically given here. We could note that if we had a 300 megahertz instrument being used, the signal of 2181 hertz on top of 300 times 10 to the 6th hertz gives us this 7.27 value for our delta. But notice that it's times 10 to the negative 6. So when we divide our frequencies, we can see that it's in 7.27 per million, per parts per million, because we have that times 10 to the negative 6. So that's where the unit of ppm comes from. So we actually would say that our shift for that proton within benzene, as observed previously on the 300 megahertz instrument, would produce that same signal, even if it was taken using a less powerful instrument, the 60 megahertz. We notice that the ratio of the signal to the frequency of the instrument is still the same. So the shift is relative to TMS, the delta value. This will remain constant no matter what type of instrument is being used, what frequency. So again, this is how the device calculates the chemical shift for us. And we will note here that our delta, our shift relative to our zero, our TMS, is considered dimensionless because hertz will cancel each other out. But we do use parts per million because we know that it's a hertz per a million hertz based on the frequency of the instrument. So in general, we can note here that a shift will occur. So this is specific to proton NMR signals. These will be between 0 and 10 parts per million. And then again, depending on the different environment, we're going to see signals utilizing this low field strength downfield. So these are in this region here where we see 6, 7, 8 parts per million chemical shift, or we have a high field strength or upfield signal that shielded protons will experience, and that's closer to our TMS standard. So upfield, you are closer to that zero marker. And we can see that these shielded protons will require a stronger external field to be excited as the same energy as deshielded protons. So that's why they have that chemical shift that's a lower ppm value. So now, utilizing the current strategy for NMR analysis, a constant field strength is applied over a range of energies, and we generate this type of spectrum shown below, where we have our TMS here at our 0 mark. We have our upfield or shielded protons that are producing these lower ppm signals, and then we have our deshielded protons occurring in this range, so closer to 6, 7, 8 ppm. So again, the higher energy we refer to as being downfield and lower energy being upfield. So some chemical shifts that you can start to familiarize yourself with for alkanes specifically are shown here. So we have methane, and we see all 4 protons would give an equivalent signal at 1 ppm. Here we have 3 protons producing a 2.2 shift. And then we have, as we get further and further along here, so we have bromine, a slightly more electronegative atom. We can see that these electronegative atoms cause deshielding, and then our signal increases. So we have chlorine, and then the most electronegative for fluorine here, we can see these protons would produce a signal around 4.3 ppm. So again, because of this deshielding effect by these electronegative atoms, we can see this signal being shifted downfield. And we can also see this extends. So the first carbon atom connected to the chlorine here has 2 protons, and their signal, again, would be the highest, that 3.3 delta. And we can see that these 3 protons, again, of that CH3 over here, this group here, these would all produce about a 0.9 ppm. So that is the 3rd carbon down. So that's our gamma carbon. So our beta carbon somewhere, those 2 protons would be somewhere in between. So again, that effect carries. Also, depending on the type of proton that we have to start with, that can also be a starting point for our shift calculation. So for example, if we have a methyl proton, we can see that the ppm, the shift, would begin there. So we can adjust our shift accordingly. Then if we have a methylene or a CH2 group, that's shown in the middle, we would start at around 1.2, and then a methine, so just a CH, where that carbon is bonded to 3 other things, and then the single proton, that would be around 1.7 ppm. And then we can also see in all of our calculations, we would include the neighboring functional groups as well. So whenever there's an oxygen present, so either an alcohol or ether in the vicinity, so this would be our alpha proton or our alpha carbon and then the alpha protons here, to that oxygen and an alcohol, we would add 2.5 to whatever our starting is. So we have our methylene group here, so CH2. So you can see 1.2 plus that oxygen value of 2.5 gives us approximately 3.7, and that's the actual observed chemical shift. So that's a very good approximation. But we can see here with the oxygen of an ester, we add 3.0 to these protons, also in a methylene group. So we start with 1.2, then we add 3.0, and we can see that our shift is still pretty close, but not exactly the same. And these are for alpha protons, but it's noted down here that beta protons would experience about 1/5 of the effect. So What is that? About zero point 0.5 for our first scenario, the oxygen of an OH or an ether, and then 3 divided by 5 is about zero point 0.6. Shift, again, this would be for an ester. Beta proton specifically. So don't forget to add these values to your beta protons if you need to calculate the approximate chemical shift for those. Here's one more useful table. All of these are found in your textbook and can be utilized on tests or quizzes. So a carbonyl group being nearby. So here's the carbonyl and then the carbon next door. Those two protons, we would add about 1.0 part per million, and they began at 1.2. So we can see again the approximation is close, and that can help us if we're determining what structure is represented, such as a ketone, aldehyde, ester, and as we saw before, alcohols, ethers. Depending on the shift that we calculate, we can expect to see different structures. There's also this anisotropic effect that can occur. This is showing in a ring structure, such as like a benzene ring here. These pi or these electrons are in this pi system. When they are subjected to an external magnetic field, they begin to circulate and produce a magnetic field, which we refer to as this diamagnetic anisotropy. So again, we can see that magnetic field applied and this circulation occur, and then this induced deshielding from this magnetic field. And the result of this is that regions outside of this ring will have an increased magnetic field, and this can affect the signal that we see. So if aromatic protons experience this diamagnetic anisotropy, they can see an effect similar to deshielding for aromatic protons. So these protons would be around 7 parts per million, right? They require more energy to do their spin flip to go between the alpha and beta states. So therefore, we see this signal around 7 parts per million. We can see an elaboration, another example of this diamagnetic anisotropy. If we have protons on the inside of a pi system, so we can see shielding here now, and the protons inside the ring would appear around -1, so below our 0 ppm of our TMS standard. Because we can see that again, this shielding effect inside our ring, whereas out here we see they were deshielded and we saw about 8 or so parts per million. So in summary, you should begin to look at tables like this in your textbook and equate yourself with the starting points when we begin to calculate chemical shift, whether we have a methyl proton, a methylene, or methine, and then these different environments that are very common. So allylic, an alkenyl proton as well. And then we have an aromatic methyl proton as an example here. So get to know these general shifts, and when you're doing the practice problems, that will come in handy and save you some time.